Hi everyone, we are back and we are about to go through our PSET 1 solution videos. So we'll pick a color and go ahead and get started. So we're going to actually go ahead and start with, remember, note this PSET correction. So we're going to look at this paper about high entropy alloys. So your traditional alloys are like alloys of metals like steel, for example. Steel is composed of iron and typically carbon or maybe some chromium or, basically several different elements that are combined, but just a few typically. 3 or 4 titanium, 6 aluminum, 4 vanadium is a very, very typical alloy. But there are these new materials that are being developed and that have been developed for a while now, which are high entropy alloys. So they utilize and essentially harness this idea of entropy in order to mix and basically create stable structures like this. So your typical alloy versus an alloy that's high entropy that contains multiple components here. So A, B, C, D, E, F, et cetera, et cetera. So, and it leads to very unique properties of these systems. So, for example, you can look at some of the microstructures, some of the applications effectively that you can start to. They have lots of different and very, very unique mechanical properties, as well as lots of different other properties as well. So how do we fill out our materials tetrahedron for this? So let's go ahead and draw it. So our materials tetrahedron can look something like this. And then like this, then like this, and like this. I'm going to zoom out a little bit. So we have, for example, we have processing, we have structure, and we have performance, and then we have here properties. So I perform a process, meaning I mix A, B, C, D, E, F elements together. I create a structure now in my system that's a high entropy alloy, which has A, B, C, D, E, F integrated into my structure. This changes properties. So for example, like my yield strength increases, my Young's modulus increases, I have different improved mechanical properties, and then that leads to an increase in performance of my mechanical performance. There's also some unique magnetic properties as well, but this is effectively the idea when we want to kind of put this together. I do a process, so I perform a process, or we perform a process, that changes the structure, which influences properties and performance. Or we see a change in properties and performance, we look at what was that structural change, the microstructure that led to that change in properties. One of the mantras that we're going to kind of say at the beginning of this class over and over: structure dictates properties. Structure dictates properties. And we're going to see it over and over and over and over again. All right. Classify whether each statement below is true or false. If false, correct. Metallic bonds exhibit delocalized electrons that can only occur between metallic materials. Yep. An electronegativity difference would classify as a covalent interaction. I would say put pure, like a pure covalent, so not at all like no polar covalent aspect to it whatsoever, but pretty much true. To investigate micrometer length scale, I would utilize a wavelength on the order of 1,000 nanometers. 1,000 nanometers is, if I move it back, that's about 1 micron. So, yeah, that's true. Steric interactions are a type of intermolecular interaction which can be broken and reformed at room temperature. That is indeed true. Bragg interaction requires a regular array of obstacles, wavelength the order of spacing of the obstacles, perfect. All true. So remember, don't be tricked. I do, true, false. Again, there's not going to be a pattern effectively. All right. Covalent interactions are intermolecular interactions in the order of 100 kT. No, it's intra. KT as units of Kelvin. Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. So if I multiply K times T, which is temperature, so the units would be joules per Kelvin times Kelvin. Those cancel out. No, those are units of energy. H bonds have completely delocalized electrons. No, they are localized. They're intermolecular interactions as well. Localized electrons are indicative of metallic bonding. Nope, it should be delocalized. CaCl2, Ca is an anion with a charge of -2. Nope, it is a cation with a charge of +2. The Lennard-Jones potential is a great potential to model metallic bonding. Nope, it is actually for van der Waals. Excellent. All right. So let's go ahead and answer this next question. What types of bonding will be exhibited by ZR? Zirconium is a metal, so it'll be metallic bonding. Will they break and reform at room temperature? No, because it's intramolecular, and they are delocalized. PCl5. Let's go ahead and look at our periodic table. So I know that chlorine has an electronegativity of 3.16. That's in our periodic table right here. We know that for phosphorus, it's 2.19. If we subtract those, it's 0.97. So that is going to be a polar covalent. It will not break and reform at room temperature, and it is localized for the electrons. And nylon 6,8, we could look at those. Let's look at the structure. This is a structure of nylon 6,8. So you have carbon double bonded to oxygen here, carbon, hydrogen, hydrogen. So we see we have intramolecular covalent bonding across the backbone of our polymer, plus this amide group, and that leads to hydrogen bonding. So we have a mix of intra and intermolecular bonding. So the inter-H bonds can spontaneously break and reform at room temperature. All right. In this crystal, what's the cation? V. What's the anion? O. O is -2 charge. So if I have 7, let me just erase that here. If I have 7 oxygens, then, and there's only 2 vanadium, so this needs to be +7 charge. Because this will be, there's 7 of those, it'll be -14. So if I have 2 of those, even. MgO, Mg will be 2+, O will be 2-. What about MgCl2? Mg will be 2+, Cl will be -1, but there's 2 of them. Charge balance. Excellent. So now we want to look at a Lennard-Jones potential. So let's go ahead, and I'm going to, let's see what we can do here. The best visualization purposes, because I want to keep the question up. I want to zoom in just a little bit here. So let's say Lj is equal to 4 times epsilon times sig divided by r to the 12th minus sig divided by r. Oops, here we go. Sig divided by r to the 6th. So we have that. Let's go ahead and define. We're given sig equals 3 times 10 to the -10. We're given epsilon equals 0.87 electron volts. We don't really want to keep it in electron volts because eventually we want to work in SI units. So I'm going to multiply times 1.602 times 10 to the -19 to convert that to joules. Because if we're asked about force or values, then I want to make sure that we're okay there. So let's look at this numerically. Good. So now I'm going to, what's the equilibrium distance? So the derivative of Lennard-Jones with respect to R. Then let's solve and set this equal to 0. Solve. And solve it for R. Because again, the equilibrium distance will, when we minimize our potential, so let's remember what we're looking at here. So when we're dealing with a Lennard-Jones potential, ULJ, as a function of R, so we see here and then here. This is our equilibrium distance, and this will be equal to 2R. So whatever that distance is of the metallic radii, or the radii in general. So let's see what we've got. We don't have imaginary values. We don't want negative values. So this will be our equilibrium distance. I'm going to call it R naught, and I'm going to solve R naught set equal to 2R. So let's solve from our metallic radii. Our metallic radii is about 1.68. We could look through our periodic table, actually, and see 1.68. What's the value here? That is PO, but that is a covalent radii. But it could be, again, that could be a material that we would look at. Typically, we're dealing with metallic materials, so we want metallic radii, but polonium, that could work. So it could be PO, possibly. But anyways, so that could be the material. Where is force maximized? So we know that force equals minus derivative of ULJ with respect to R. What's our potential? Oh, we just said LJ. LJ with respect to R. If I want to figure out where is force maximized, solve when the derivative of force with respect to R equals 0. Should be larger than the 3 point. It should be larger than our R naught value based on our value, and that is indeed the case. Excellent. What values of interatomic distances will the atoms repel? So if we look over here, if I'm looking on this side, if the atoms get closer together, my potential actually, well, it increases either way a bit. But here, the atoms are going to want to minimize. If I jump this way, my energy increases. They're going to want to actually move further apart to lower my energy. So on the left side here, we're repelling. Here, we're attracting. And we could kind of relate that to the forces. So for example, we know what our R naught is. So I could look at force / dot R goes to, let's say I'm at 3 times 10 to the minus 10. The force here is positive. So what does that mean? What direction is it pushing? So I'm looking at my interatomic potential here and here. So it's looking at what are the forces between them. So are they pushing like this, or are they pushing like this? So my interatomic potentials, if they're pulling them apart, that's basically they're saying they're repelling. So it's the force between my atoms. So a positive force would mean repelling. And we see that. That is indeed the case. So they are basically pointing in this opposite direction, not pointing towards each other. So we're pulling them apart. If I look at something where force / dot, if it's on the other side of this R naught, so force R goes to, how about 3.8 times 10 to the minus 10. And that's negative. They're going to be pulling each other back together. So there we go. That is it. That is your problem set 1. So we'll see you in the next video for problem set 2. Thanks. Bye.